For this video, allow me to use the substitution process or method and go away with the use of the limit theorems so that we will able to show the solution or the result for this immediately. Now, of course, we have the previous 3 videos with the use of the limit theorems. At the same time, we also have the discussion of the limit theorems themselves, and even you can use the limit theorems here as well. But allow me to use the substitution to make this clearer and shorter. So you will have here the limit of your complex function z squared minus 5z plus 10 as z approaches 1 plus I. Okay, so by limit theorem, you are going to distribute that, right? The limit of your z squared as z approaches 1, sorry, that's 1 plus I, and you have your minus the limit of your 5z as your z again approaches the same, 1 plus I, and you have here plus the limit of your constant 10 as z approaches 1 plus I. And you are going to solve them step by step, which would actually take 1 or 2 more steps than the direct substitution that we're going to use here, meaning we're going to substitute immediately the value of our z or z sub 0 to this and that portion. That would mean you will have this form here. This is equivalent to, you have 1 plus I squared minus 5 times 1 plus I, and then you have here plus 10, which is actually just the same as these 3 methods here. So I'm not going to show again the derivation of this or the final form for that, because I would like to focus now on this portion here. We have the square of a complex number. It's very important that you can illustrate that carefully. So you have here 1 plus I squared, which is equivalent to 1 plus I times 1 plus I. You can of course apply the squaring of binomial, but I'm using this for the benefit of those who would like to see the proper step-by-step process. You have 1 times 1, 1. Outer terms, you have your I. Inner term plus I. And your last terms, rather, you have your I squared. Take note that this I squared, okay, is equal to -1 because I is square root of -1. Okay, take note of that. That would mean this is equivalent to 1 plus 2I as the sum of this. And then you have here plus -1. Of course, these two would be cancelled. So the result for the first term, again, just the first term is 2I. And that's this first term here. This is now equivalent to 2I. Okay, we don't have the rest other value for that because we have simplified the terms or the real parts earlier. Then, to continue, you will have the next term here. So minus 5, then you have minus 5I. As we are distributing, okay, this to that. And you have here plus 10 as well. So what would be the final answer here if you're going to combine all the real parts together with the corresponding real parts, of course, and if we're going to combine the numerical coefficient of the imaginary parts. So you will have here the form 2I minus 5I is -3I, and -5 plus 10 is plus 5. This is now the limit of the given complex function z squared minus 5z plus 10 as z approaches 1 plus I. Again, this is even true when you are going to use the limit theorems, but of course they will just reach to that. So again, 1, 2, or 3 steps less, as long as you can guarantee that your substitution is actually accurate. Take note that substitution may not be always true, especially for some types of functions, such as, say, for example, piecewise function, in some instances where we cannot do that. Of course, let's try to finish this by the rest of the process, taking notice this point of view here, which is this one here, and carefully combine all the rest. Or of course, before we end, just to be similar with the rest of the answers, let's start writing this with the real part, which is 5. That's -5 plus 10. And you have here minus 3I. Okay, I forgot to really notice that my final answer is not expressed as x plus iy. So it's there just the same, but let me express it this manner so that we will be consistent with our complex numbers. Thank you very much for watching.